Albert Einstein's theory of relativity made a lot of people very unhappy. Revolutionary ideas are magnets for controversy, especially when they force us to completely revise the way we see the universe. Its reception by the vast majority of Einstein's fellow physicists was frosty. Absolute space, absolute time, and the luminiferous ether that carried light waves through space were central parts of the picture that physicists have been trained to accept their entire careers. And here they were rejected by a theorist who, at the time, was not even a working scientist. Einstein was a patent clerk in Bern, Switzerland, a civil servant working in an office when he published his original theory of relativity. Some physicists rejected it vociferously. Some withheld judgment, but most simply ignored it. It was too strange, too radical. You don't just throw away the foundations of your entire worldview for every strange theory that gets published, even if it does appear in the leading journal of the time. Indeed, physicists were not the only ones objecting. Philosophers wrote articles condemning the effort to jettison notions they took as necessarily true of the universe, or at least of our minds working and creating what we think of as the universe. Political enemies labeled it scientific Dadaism, connecting modern physics to modern art, both of them presenting bizarre images they claimed to be meaningful. Relativity, they said, was Jewish science, an effort to undermine the ideals on which traditional culture and values were based. Humans take the process of redefining reality very seriously. It rarely happens without a fight. Interestingly, one of the people unhappy with Einstein's theory of relativity when it was formulated in its original papers in 1905 was Albert Einstein himself. He thought there were two significant problems with it. First, the theory was limited. The theory of relativity showed that different perspectives had equal access to reality. But the theory of 1905 only extended this right to perspectives connected to observers who were moving in straight lines at constant speed. Accelerating reference frames weren't properly connected. Second, the theory of relativity, as Einstein initially set it out, mentioned every known force in the universe. Almost. There was one missing: gravity. It seemed odd to Einstein that gravitation was somehow not present in the theory. Physics should be a unified endeavor, all of the elements woven seamlessly into all the others. Somehow, gravitation would need to be shown as a part of the theory, but not in an artificial, add-in sort of way. Gravitation, the force that literally holds the universe together, needed to be an organic part of the new view of reality. And so, the original theory became known as the special theory of relativity, and Einstein began a search for the general theory of relativity. Now, in common everyday talk, we prefer special to general. It's good to be special. Everyone's mom thinks he or she is special. It's good to be chosen for the special group and not part of the general population, the normal folks, the unremarkable among us, the rabble. But in science, it's the other way around. Special means it only holds for a special case, a limited number of situations. What we want from our science are general truths, universal laws, propositions that hold true no matter what, where, when, who, or how. Einstein saw his original work as descriptive of space, time, and motion in a universe without gravitation. The problem, of course, is that as soon as you have an object with mass in the universe, you have gravity. Einstein's redefinition of reality held, in essence, for a completely empty universe. That, of course, is not the universe we inhabit, and so the theory would need to be reformulated. Turns out, this was hard. Really hard, even for a genius like Einstein. He quickly realized that his general theory would make his original one look like, in his words, child's play. And so he struggled until he had what he called his happiest thought. He was looking out at some window washers high up on his building. Allowing his mind to wander, he thought about one of them falling off his ladder. Now, a normal person thinks about a person falling off a ladder and instantly thinks of the crash landing, all the pain, the consequences for the person and his family, and the result of the injury. Not Einstein. When Einstein thought of a man falling off a ladder, he concentrated on the falling. What would it be like, from a physical point of view, to be falling? what laws of nature would govern the interactions of the objects around the person falling? Einstein realized that while the man is falling, because of gravity, while he's falling, he would not experience any of the usual gravitational effects. Objects around him would seem to float as if there were no gravity. He would feel weightless. When accelerating in freefall, it's as if there's no gravity at all. This was Einstein's happiest thought. It was Einstein's happiest thought because it simultaneously answered both of his problems with the special theory of relativity. Remember what he was worried about. 1, the fact that the accelerating reference frames were ruled out, and 2, there was no gravitation in the theory. What thinking about the man falling off the ladder showed him was that they were related. The way to meld gravitation into the theory was to connect it to acceleration. The two would be flip sides of the same coin. This is what Einstein called the principle of equivalence. Now, imagine you're in an elevator with a bathroom scale. Why do you have a bathroom scale in an elevator? Don't ask. You get on the ground floor, and before the elevator starts moving, you step on the scale. What does it show? Your normal weight, or in technical terms, a little too much. Now, push the button for the 19th floor. As the elevator starts going up, what does the scale read? Even more than before. Why? Think about how a scale works. Now, normally, you stand on the scale and your weight pushes down from above. The floor holds steady below, and so the springs inside squish, and the amount of squish is read off by the dial showing your weight. As the elevator goes up, you're still pushing down on top, but now the floor is pushing up from below. This means more squish in the spring, and the weight displayed increases. Now, suppose when you reach the 19th floor, the unthinkable happens. The chain snaps, and you're sent hurling down the shaft. In your last seconds, you look down at the scale. What does it read? 0. Why? Now, you're still pushing down on the scale, but now the floor is falling away at the same rate you are. So there's no squish in the springs. It displays 0. You are effectively weightless as you fall. Let's consider a different scenario. Now, suppose instead of an elevator, you're in a rocket in an empty region of space far, far away from any massive object. So there's effectively no gravitation. Right? You step on the scale, and what does it read? Well, of course, 0. Right? You have weight on Earth because of Earth's gravitation pulling you down. No gravity, no weight. Suppose you're out in empty space in your rocket and you fire up the engines so that the rocket accelerates upward. What will you experience? A pull downward, right? You're floating, but the floor is now pushing up against you. Now, if you accelerated at just the right rate, increasing your speed by 32 feet per second each second or 9.8 meters each second, and then stepped on the scale, what would it read? Your weight on Earth. So, you wake up tomorrow in a small metal room with no windows and nothing but a bathroom scale. Could you tell whether you were on Earth in an elevator or in space in a rocket? If you stepped on the scale and it read your normal weight, you might be at rest in the Earth's gravitation, or you might be accelerating in empty space. If it read 0, you might be accelerating in the Earth's gravitational field, or you might be at rest where there's no gravity. There's no way to tell the difference. Here, Einstein borrows a principle from the 17th century German philosopher and co-creator of calculus, Gottfried Leibniz. It's what Leibniz called the identity of indiscernibles. If there's no difference between two things, they are, in fact, the same thing. If there's no way to tell the difference between A and B, then A and B are the same. William James put it this way: a difference that makes no difference is no difference. But if there's no difference between our elevator and rocket ship cases, that means that gravitation and acceleration are just different ways of describing the same thing. Einstein would take this as the basis of his new theory. But there does seem to be a way to tell the difference. Maybe not stuck in the room with the scale, but maybe if we allow for more data. So here's an idea. Poke a hole in one wall of the metal room. Now what's going to happen? Any light from outside will come through the hole. That light will travel across the room, and a bright spot will appear on the opposite wall. If we have a ruler, we can measure the height of that light spot and the height of the hole. Suppose we've stepped on the scale and it reads our normal weight. Now, we're trying to determine if we are at rest close to the Earth in our normal gravitational context, or if we're accelerating upward in a region of no gravity. We can measure the height of the hole and the height of the light spot on the wall. The thing about light is that it always takes the shortest route between 2 points. And we know from Euclidean geometry that the shortest distance between any 2 points is a straight line. If we are at rest, we would then expect the dot to be directly across from the hole because the light took the straight line out of the hole to the wall. But if we're accelerating, we would expect the light dot to be lower than the hole because the time it took the light to move straight across the room itself would have moved up. From the vantage point of someone in the room, it would look like the light rays curved down. So, we poke our hole and we see if we have straight or curved light. If the spot is at the height or below, that should tell us if we're accelerating in no gravity or not accelerating with gravity. But Einstein pointed out that this line of thinking made 2 important assumptions. First, that light moves along the shortest possible route. That one he'll grant. And second, that the shortest possible route is always a straight line. That one he won't grant. If we want to maintain the equivalence, then we need to surrender the idea that the shortest path between any 2 points is always a straight line. Now, in flat space it is. On a chalkboard, take any 2 points and the shortest distance between them, always a straight line. But if, on the other hand, you were restricted, say, to the surface of a smooth globe, this isn't true. The shortest path between any 2 points on the equator of the Earth, when represented as a perfect sphere, is along the equator. And that's a curve. For Einstein to make the move that solves his acceleration and gravitation problem at the same time, he has to posit that space, or following the special theory of relativity, space-time, is curved. Now, this was a problem for Einstein. Not because he was married to the old idea of flat space. He had no problem challenging our picture of the underlying reality. The problem was technical. He had never learned the math needed to work in curved spaces. It baffled him. So, he did what he always did when he had a problem. He went to his best friend, Marcel Grossmann. When Einstein had exams in college and suddenly found he had no idea what was taught because he didn't show up or take notes in class, Grossmann let him use his notes and they earned the top 2 marks. When Einstein couldn't get a job because of lousy references from his professors, because he didn't show up or take notes in class, Grossmann got his father to find Einstein a job at the patent office. Grossmann was always there to bail Einstein out of the messes he constantly created for himself. Now Einstein was in a jam because he didn't have the mathematical tools he needed to do his physics. Grossmann? Yeah, he just happened to have recently finished his PhD in mathematics, and wouldn't you know it, the topic just happened to be the geometry of curved spaces. Grossmann told Einstein that he had just what Einstein needed, but shook his head and said the problem is that the mathematics needed is very difficult, perhaps too complicated. Physicists, he told Einstein, might not be smart enough to understand it. But with Grossmann's tutoring, eventually Einstein caught on. The result is a theory in which gravity is thought to be the curvature of space by mass and energy. Now, in the old theory, Newton's picture of the universe, we had separate space and time. Time was perfectly linear and space was perfectly flat. In this space was a force, gravity, acting between all objects but not affecting the underlying space. Space, for Newton, is like an infinitely long and infinitely wide frictionless pool table. Because it's infinitely long and infinitely wide, the balls would never reach the rail and change direction. Because it's frictionless and flat, the balls would never speed up or slow down because of the table. Space is just where things are and not affected by them and has no effect on them. For Einstein, on the other hand, gravity is not a force between objects, but an interaction between space and objects. Matter and energy tell space how to curve, and the curvature of space tells objects how to move. We need to account for two basic motions that come from gravitation, right? Straight in for objects close by the source of gravity, and periodic orbits for those farther out. To see how the curvature of space accounts for both, picture space not as Newton's infinitely big frictionless pool table, but rather as a trampoline. Now, if I put a bowling ball in the middle of a trampoline, what happens, right? It sinks into the trampoline, causing a curved surface around it. Now, if you and I are on opposite sides of the trampoline and you try to roll a tennis ball across the surface to me, right? Let's think about what happens. If it goes straight towards the bowling ball, it speeds up going in and slows down coming out. If it were not rolled hard enough, it wouldn't make it out, but would roll straight back down to the bowling ball. Now, if the tennis ball were not rolled right into the curved area, but close by, the path would curve. Exactly what we see with comets, for example. If it were rolling at the right angle close enough, the result would be a circular orbit. Think of those large spiral funnel coin wishing wells, right? You can find at the mall or the grocery store. Right? You know the ones where you release the coin on the side and it rolls around and around? This is another model of Einstein's space near a massive object. Now, the reason the coin spirals down and down and down into the hole is friction. The surface removes energy and the coin slows down and the radius becomes smaller and smaller. But if we think of a frictionless version, right, grease it up really good, the coin would forever circle around the central hole, which is just what we see with planets and moons. If Einstein's right, and space is curved by matter and energy, we could account for the gravitational phenomena we observe in a way that makes gravity a natural part of the theory of relativity and accounts for the accelerated reference frames Einstein left out in the special theory. But is he right? Does space curve around massive objects, or, as Newton posited, is space flat? This was a testable proposition. One test involved the planet Mercury. Now, Mercury's orbit had confounded astronomers for decades. Since Kepler, we knew that the orbits were elliptical ovals, right? We knew that the gravitational effects of other planets, however, made them messy ovals, but they were ovals. Mercury did something weird. It went in an oval that never closed. The point of the orbit farthest from the sun advanced a little each time around. So the oval orbit itself orbited the sun. Scientists tried to account for this using Newton's theory with all sorts of twists and tricks, but no one could ever do it. Einstein applied his general theory of relativity to the case. The theory nailed it. Perfectly accounted for the strange orbit of Mercury. He describes the moment when he realized the result. He said he felt like something inside of him burst. He was so overjoyed he couldn't concentrate on physics for a week. For Einstein, that's a big deal. But while it convinced Einstein, the rest of the physics community needed more evidence. If space bends, then light follows curved paths. But this change is so slight that you would need to see light pass by something huge to notice any effect. The only thing close by that's of sufficient size is the sun. The problem, of course, is that the sun is bright. You can't see light passing close by the sun because the sun's own light washes it out. But there is a time when the sun's light is blocked. That's during an eclipse. So, the British astronomer Arthur Stanley Eddington was placed in charge of a project that sent 2 expeditions out to observe the eclipse of 1919. One in South America and one off the coast of Africa. We knew what the sky would look like if the sun were not so bright. It's what the night sky looked like 6 months earlier when we were on the other side of the sun. So, when the eclipse occurred, we knew precisely what star should be just next to the blocked out sun. If Newton is right, that star should appear right where it's supposed to be. But if Einstein's right, that star should be shifted slightly, its light bent by the gravity of the sun. Eddington's team took photos. The data was analyzed, and Einstein was spot on. Word was sent immediately to Einstein in Germany. He opened the telegram, read it, and calmly handed it to a graduate student who was meeting with him at the time. She read the news and knew what it meant. Einstein had changed everything. The evidence was in. Yet, the man was completely calm. Shocked by his placid demeanor, she asked, what would Einstein have thought if the results had been different, if Newton's predictions had been the ones that were verified? He looked at her and said, I would have felt pity for the dear Lord. The theory is right. No one ever accused Albert Einstein of excessive modesty. The idea that space is curved captured the imagination. It's responsible for much of the long-distance travel in contemporary science fiction. Hyperspace in Star Wars, subspace in Star Trek. If the special theory of relativity is correct, and the greatest speed attainable is that of light, then most of the universe would be inaccessible to beings with a limited lifespan. So, if we're going to explore the greater universe, we need to travel faster than the speed of light, but that can't be done. Or can it? The key to these sci-fi fixes is to realize that when Einstein says space-time itself is curved, we're not talking about a surface in space, but space itself. When trying to picture this, we use the example of a globe, right? That is a two-dimensional surface on a sphere that resides in a larger three-dimensional world. But for Einstein, there is no bigger universe in which the universe is set. It's space-time itself that curves in the presence of matter and other forms of energy. This is hard to picture, but the thought on the part of science fiction writers is that if I want to get from one place on the Earth's equator to another, I could follow the equator following, the shortest path on the surface of the globe. Or I could tunnel through the Earth and create a straight line path that would be even shorter. By analogy, if space-time curves, I could follow the path light takes, the shortest path in space, or maybe I could tunnel through space to create a straight line and a shorter path. This would let me move faster than light and allow, in principle, for travel to otherwise inaccessible regions of the universe through such wormholes or hyperspace as we find in Star Trek, Star Wars, and Doctor Who. Each of these, of course, has its own way of creating and massaging the route through a non-existent trajectory in space. I'll leave it up to their respective fan bases to hash out which is most likely true, given our best theories of space-time and motion, gravitation. You'll find this a topic on which much conversation exists, much of it on the internet. But we don't need to resort to science fiction to find peculiar effects. We realize that strange things could happen if we pack enough mass and energy into a small enough area. The space would warp so severely that straight lines would actually curve back in on themselves. Light that went into the area would never re-emerge. Emitting no light, it would be completely black. Sucking up passing light, matter and energy, it would function as a hole in space. Thus we call it a black hole. The idea of a drain in space, which sucks in everything around it, is strange enough, but it gets weirder, because it's space and time themselves that are warped. Surrounding the black hole is what we call an event horizon. It's the border of the black hole. Anything that crosses it cannot re-emerge. You'd have no sense that you crossed the event horizon if you were the unfortunate traveler. There's no sign, welcome to the event horizon. But those of us watching you would experience something peculiar. Remember that relativity includes an effect called time dilation, according to which time slows down when measured by a fast-moving observer. Because of time dilation and the curvature of space-time, when we out here watched you approach the black hole, you would appear to move slower and slower the closer you got to it. Right around the event horizon, time appears to stop to those outside. This is why an early Russian term for black holes was frozen stars, because around them, time seems forever frozen. There's a famous problem with black holes. We came to realize that the solutions to Einstein's equations that yielded black holes predicted that at the center would be what we call a singularity. The problem is that the curvature of space is measured as a 1/x term. And if we do what physicists love to do and treat objects as point masses, that is, if we ignore size and shape of mass, which makes the calculations much more difficult, then the term x in our 1/x measure goes to 0. This means that the curvature becomes infinite. We're not even sure what that means. But more importantly, recall that 1/0 has no meaning in our mathematical language. Right? 1/2, 1/2, means we've cut the pizza into 2 slices and taken 1. 3/4, 3/4 means the pizza's cut into 4 pieces and we've taken 3. 1/0 is meaningless because we can't cut a pizza into 0 slices. But here's a result of the equations of the theory that give us an answer that cannot be connected to a reality. If a theory gives us an answer that's impossible, we have a problem with the theory. Einstein's theory of general relativity seems to describe a reality that can't be real. Physicists have taken 3 approaches to this problem. First, we can simply ignore it. It may be an artifact of the theory, but since it's mathematically unrealizable and present only at a single point, which has no size anyway, maybe it's just a glitch to be overlooked. The earliest discoveries of singularities and solutions to the general theory of relativity were shown to be caused by oversimplifications in the presuppositions. They could be eliminated by simply adopting a new perspective from which to view the system. They weren't real, just a result of how we set up the reference frame. It was a trick of the math, not something actually described by the math. If this was true for the first singularities, maybe it'll be true of the ones we see now. The second approach was that of Eddington, who brushed it under the table. To the Indian physicist Chandrasekhar, who won a Nobel Prize for his work on black holes, Eddington famously said, "I think there should be a law of nature to prevent a star from behaving in this absurd way." In other words, the theory is right. Singularities can't exist. Yeah, we'll sort it out in time. Singularities show up in non-rotating black holes, so perhaps we'll find something that forces them to rotate. The third approach is to say that the theory is problematic, that it needs to be augmented. We need another theory: quantum mechanics.